Hey friends, what's good? Thanks so much for visiting. I hope this video will be what you're looking for. Looking at NetPractice myself, I had no clue what I was doing and had so many WTF moments. Hopefully making this video will solidify the things I've learned and help you out too if you're struggling with NetPractice. I want to preface by saying that I'm not an expert and this is the first time I'm learning about networking and I'm still learning. So please let me know if I make any mistakes in this video and I'll pin them to the comments. This isn't a comprehensive guide to networking. I'm only going to be sharing specific things that personally helped me to pass NetPractice. And you might have some questions unanswered in this video. Even I still have questions, and doing your own research is encouraged. Included in the video description below are links to some videos that have really helped me learn about networking, so do check them out. In this video, we'll be exploring some networking concepts applicable to NetPractice from my perspective. What I mean by this is everyone has their own way of learning, right? And so my way may be different to yours. I'll be sharing some tips that personally helped me complete the exercises, but you might have your own preferences. And finally, we will be walking through a NetPractice assessment, which will consist of 3 random exercises. The subject PDF tells us that we need to understand how TCP IP addressing works, which is a motherlode. It doesn't really tell us specifically what we need to learn about networking, and logs are also provided for each exercise, but these didn't really help me understand what was going on either. Maybe for you, you'll find it helpful. So I'll be talking very briefly about TCP and IP addressing because to pass NetPractice, I didn't have to delve too deep into this. What I really wanted to know was what's a LAN, an IP, a subnet, switch, router, and gateway. So what is TCP IP? It's really just a list of rules for how data should be sent and received between devices. These standards are divided into layers. So the application layer is where end user software operates, for example, web browsers and email clients. The transport layer is responsible for end-to-end communication, for example, ports, which are numerical identifiers used to distinguish between different services or applications running on a device. There's an internet layer that manages addressing and routing of packets. And there's a link layer which handles the physical transmission of data over a network. So, for example, Ethernet cables. A LAN is a local area network. It has a network of devices talking to each other within a limited range. For example, your home network has multiple devices connected with each other and talking to each other. And IP is short for Internet Protocol. It's an address of a device in the network allocated by a router. IP addresses helps identify and locate a device on a local area network. And more importantly, IP addresses help devices talk to each other, like how mobile phones have phone numbers and houses have street addresses. Every device has a unique IP address, and the 2 main versions are the IPv4, which looks like this, and the IPv6, which looks like this. We don't really need to worry about the IPv6 for NetPractice, only the IPv4. In this example, each of these are called octets. So an IP address has 4 octets separated by dots. The first 3 octets here is called the network portion, and the 4th octet is the host portion. A host just means a device like a phone or a computer, etc. A host will always be assigned a usable IP address, so this means within a network there will always be two IPs reserved and unusable. We cannot touch it. They are the network address, which is the first IP of a network, and the broadcast address, which is the last IP of a network. The usable IPs in this network will begin at 192.168.1.1 and end at 192.168.1.254. This means a host within this network can be assigned at the host portion of an IP anywhere from 1 to 254. And there's a reason why an IP address range is however short or long it is, and we will explore why a bit later on. Let's look at assigning IP addresses to hosts in this local area network. Let's say for this device, which is a switch, and we'll talk about what it is later, but for now we assign this device a 1 as the host portion of the IP address. We give this printer a 2, this laptop a 3, and we could give this laptop a 4, but recall for this network, the usable IP range can be anywhere from 192.168.1.1 to 192.168.1.254. So let's say this IP is 192.168.1.200. But what if we looked at another network? How can we tell whether a device belongs to a specific network? This is where subnets come in. Recall we said for this network, the usable IP range is 192.168.1.1 to 192.168.1.254 because there are always two IP addresses that are untouchable. One of those is the network address, which is 192.168.1.0. The subnet is basically the network address, which is the first IP address in the range for that subnet. So when we look at this subnet, it tells us the range of usable IP addresses in that network would be from 192.168.1.1 to 192.168.1.254. A subnet is also typically represented with a CIDR notation. In this case, it is 24. The CIDR notation specifies the subnet mask in a shortened format, indicating how many bits are used for the network portion. Earlier we said we would explore why an IP address range is the way it is, and we're about to get into that. A CIDR notation, in this case, 24, represents a subnet mask, which looks something like this. In decimal, it's 255.255.255.0. In binary, it's a bunch of ones and zeros, where the ones and zeros will always be contiguous. Each octet has 8 bits, and all the ones indicate how many bits are taken for the network portion of a subnet, making it fixed, and the zeros indicate how many host addresses are possible, which is a variable. It can be really helpful to be able to convert a subnet mask to bits and vice versa in network configuration. Before we get into this, let's do a quick recap on what a subnet is. A subnet is a subnetwork. In other words, it's a smaller network of a larger network. It defines a range of IP addresses in a network, and it helps us determine whether a machine or device belongs to a particular network. A subnet is essentially the network address, with the CIDR notation representing a subnet mask. And a subnet mask tells us how many bits is used for the network and how many hosts a network can have. Looking at this configuration, we know that all these devices belong to the same network because they have the same subnet masks. We see the first 3 octets, the network portion of each of these IP addresses are the same, and the host portion of their IP addresses tell us that they're in the same network range. Let's have a look at another example. In this example, we're given the IP address and subnet mask of the switch device. This means if we want our devices to be able to talk to each other, they all need to have the same subnet mask. What about their IP addresses? This subnet mask tells us that the network address, which is the first IP in this network, is 192.168.42.0. And the broadcast address, which is the last IP of this network, is 192.168.42.127. The subnet is 192.168.42.0/25. And this gives us a usable IP range of 192.168.42.1 to 192.168.42.126. We check the validity of the laptop's IPs and masks, and we can see that the IP addresses assigned to these hosts are valid and within range. So how do we know what the first and last addresses are and what the range or CIDR notation is for this network? First, we convert a subnet mask from decimal to binary. Each octet has 8 bits and we convert each octet. All the ones tell us the network bits and the zeros tell us the host bits. Each bit represents a power of 2, so that's 2 to the power of the position from the right. If all the bits are 1s and we summed up all the bits, then the total is 255. Suppose we have a mask of 255.255.255.240. Looking at the 4th octet, we can sum up the power of 2s from the left to see how many host bits we need. And so we need 1, 2, 3, 4 host bits. Going back to our earlier example network, our subnet mask was 255.255.255.128. How many bits do we need for this host portion? 1. The next thing we need to do is to find the CIDR notation. And that's easy because we just count all the network bits out of the total 32 bits. And we have a total of 25 bits out of 32. So what if we wanted to have more than one network? With a subnet mask of 255.255.255.128, we can have 2 networks, each with 126 usable IP addresses. This is where we need to be careful of overlaps of IP addresses. Overlaps occur when separate networks use the same IP address space, so we need to make sure to assign hosts' IP addresses within the correct subnet range. But what if we want even more networks? This is where we do what is called subnetting. We do subnetting when we want to create more networks. I learned about subnetting from Network Chuck. He explains things in such an easy to follow way. He talks about hacking host bits to create more networks. For example, we started off with this subnet, which is one network. Let's say we want 4 networks instead of 1. We need to work out how many bits we need to hack. Recall our decimal to binary chart. If we times these power of 2 values by 2, we get these values. We want 4 networks, so we look at where in these values can 4 bits fit. It fits right here, so we need 2 bits out of 8. Because the 1s and 0s will always be contiguous in binary, we hack the bits from the previous one, so from the left. Summing the bits in the 4th octet gives us 192. Now we have 4 networks, and our new subnet mask is now 255.255.255.192, giving us a CIDR notation of 26 across all the networks. Our first network address is 192.168.1.0, but what is our broadcast address? To find the size of each network, in other words, how many hosts can we have in each network, we need to find the increment of the last network bit. Referring to the power of 2's chart, the last network bit is located at 64, and 64 determines the size of our network and range. So our broadcast address for the first network is 192.168.1.63 because we include the 0, which gives us a total of 64 IP addresses. From here, we can work out the ranges of the remaining networks. To recap, let's point out all the steps of subnetting, which will help us with the NetPractice exercises. Step 1, we convert the subnet mask to binary. Step 2, we find the CIDR notation. Step 3, find the increment, which is the last network bit. And step 4, create the networks and find the ranges for each. So what is a switch? It's a device that sits inside a local area network, and it connects multiple devices within the local area network to help them talk to each other. It manages where data is sent and received. For example, let's say a laptop sends to the switch a request to print a file. The switch then identifies that the request needs to go to the printer's IP address, and so it sends it to the printer. A switch can also be connected to a router. A router is a networking device that sits between the local area network and the external network, for example, the internet. Routers operate at the internet layer of the transmission control protocol, or if you're referring to the OSI, that would be the network layer. Routers connect us to the internet and other networks. This is called the wider area network. Routers can have multiple IP addresses for different networks, and it uses routing tables to determine the best path for data to travel and forwards data packets between the multiple networks. For example, a mobile phone wants to connect to the internet, so the mobile phone sends a request to the router, then the router connects it to the internet if it approves. A gateway and router is often the same device, which can be confusing. The only difference is their function. The router routes data packets between different networks and determines the best path for data to travel based on IP addresses. The gateway acts as a gate between two networks, allowing them to communicate. It can connect networks that use different communication protocols as well. A gateway has a single IP address, which is of the router, that serves as the entry and exit point for a network. This is an example of what a NetPractice exercise looks like. The task is to reconfigure the unshaded sections if they're incorrect in order to make the network work. Once everything works correctly, the goals above will show OK instead of KO. These are some tips I came up with that helped me progress through the exercises better, though you might have your own ways of navigation that you prefer. The strategies that helped me included taking out all the noise, in other words, wipe out all the unshaded sections and start with a clean slate, like so. See how clean it looks? Well, in my opinion anyway. This way I don't get confused with what I've reconfigured and what I haven't, what is correct and what is not correct. Next, I work backwards using the provided default values to fill in where it's applicable, and you'll see what I mean later when we do a walkthrough. It can also be helpful to work through one goal at a time when there are multiple goals. This helps me focus in on one problem and not get too overwhelmed. So I'm frequently checking after each reconfiguration to see if I'm on the right track. And lastly, I use a Subnet chart. I wasn't a fan of using an IP address calculator, so I came up with a chart that I can easily write down anytime, anywhere, and I can refer to it when I need. This spreadsheet is not it, but it was how it started. By the way, does anyone know how to dark mode in Excel? Because this is extremely painful. Anyway, so after writing out this spreadsheet, I noticed some patterns, and so rather than referring to this long, extensive list, I created this chart, which is much simpler. The top row are the CIDR notations where the host bits are in the third and fourth octets, excluding the CIDR notation 24 because that's just in the fourth octet. The second row are the CIDR notations where the host bits are in the fourth octets. The third row are the bit values, which I refer to for the network increments. And the last row is the decimal value of the host portion of a subnet mask. I just need to remember that if the host bits are in the third and fourth octets, then the decimal value is in the third octet of the subnet mask. Let's have a look at some exercises together. During a defense, we leave this area blank and we get 3 random questions. So let's go ahead and select start. Okay, so the first thing I do is I take out all the noise and start clean. This is a routing table entry, and what we have here is called a next hop IP address, which is the address of the next router to receive the data packet. And this is called the destination, which is the IP address of the final destination where we want to send the data packet. We put default here, which means we're using the default route because there is no specific route for the destination, and so the data packet will be forwarded to the default gateway. So for this device, what we're saying on this routing entry is send data packets to this destination and along the way go through the router, which is the next hop IP, before reaching the final destination. We have a network here, so we know that this next hop IP is the address of this router. And we've got a CIDR notation of 18 here, which should be the same for devices in the network. Looking at the subnet chart, we know that this subnet can give us plenty of networks without overlapping, so we can go ahead and give this network the same subnet mask. We give this host its IP address. We give this router IP and address after changing the third octet. And it will be our next hop IP for this host. Now let's see if we can get host C and D to connect, which is a success. We've got a point-to-point link here that will connect this router to the router above it. And so R21 and R13 are gateways that serves as the entry and exit points for their networks. We'll go ahead and give them their IP addresses. And I'm just using 1, 2, 3 as the first 3 octets just because I'm lazy. And now we have the next hop IP for our gateway, which is the address of the next router. And we also want R13 to be able to send data packets back to R21. We have another network here, so we'll go ahead and give them all the same subnet masks. And now let's give them their IP addresses. And let's check if these guys can talk to each other in their network. And the plus side is we know that we have these different networks also talking to each other. To get host A connected to the internet, we place its subnet as the destination in the routing table entry of the internet. The reason why I put the CIDR notation here as 20 instead of 25 or 26 is really just because it's out of habit and ensuring that more networks are covered. Now we need to get host C to connect to the internet. Because we have host bits in the third octet as well, we need to make sure that we put in the correct subnet. Okay, so the CIDR notation of 18 is not enough to cover the networks, so we put in 16. I haven't looked into why this is the case, so if you can teach me about this, I'd love to know. So again, we clean up all the unshaded areas. We copy the given mask here and we paste it here. We check that this subnet mask is able to give us plenty of networks, so we can use it for the other networks too. We're given the IP address of this router. And that gives us an idea of the IP address for this router. Whoops, let's fix this. We've got a destination address here, so this means that we need to make sure that all of our hosts, our devices, are able to communicate to the internet. And we do this by using the same first 3 octets. We make sure that the routers are able to talk to each other. And we're given the router IP address for the internet here. Okay, so we've got host D and C to communicate with each other, but we're still not able to connect to the internet. Let's try using the subnet of this router as the destination instead. Which makes sense because R13 and R21 are gateways for the networks. Okay, so we have our last exercise. See if you guys can recognize what I'm doing here. So there we have it. I hope that was helpful. I'm sorry if it's not the best explanations, but this is how it all makes sense in my head. I'm going to do a few more exercises, this time without me talking, if you wanted to see more examples. Thank you so much again for dropping by, and good luck.